Assalamu alaikum. So as you asked for the Newton-Raphson test bench explanation, so here we are. As you can see, there are three inputs, x1, x2 and x3, which we have through test bench added the values for 2, 1 for x1, 4 for x2 and 16 for x3, and subsequently these are the results s1, s2 and s3. These are the square root answers, but as you can see they are not what you expect. For 2 it is 1458. For 2, as we know, if we do a square root of 2, we know it is 1.41. It is not close, not even close. So why is there such a discrepancy? So in VHDL there is no declaration for fixed point. Okay, there is for signed, unsigned, but there is no declaration for uh, floating point and fixed point. It is through how you are writing your code. Bit manipulation, for example, is one way that you write integer and fraction bits, and we can analyze the code. It will be a very long way. We analyze the code and then through our working we can find out. But the shortest way, if you are given a code and you want to find out how many bits are uh, fraction and integer, and so I'm going to show you the fastest way that you can find out. Now uh, first we have to check how many bits is the output. We can check that by looking at the top level design, and we can see this is 28 bits. Okay, the input is 16 but the output is 28 bits. Okay, so that means we are working with currently let me put up a marker, that we are currently working with 28 bits. Okay, now we have to find out how many bits are fraction and how many bits are integer. First thing you can do is, you know that the answer for square root of, for example, 4 is 2. Okay, write 2 and you multiply that by the scaling factor of the fraction bits. Okay, they can be 8, 9 bits, 4 bits, 3 bits, but let's try with for example 8. Okay, we get 512. That is not correct. Okay, there might be more, or there might be more, because the answer is 2049. So it is more than 8. Okay, let's try 9. 1024, still no. Okay, 2048. So this is now very close. Okay, now very close to our answer or output. Why this is not accurate? Because if we convert this to binary, you can see, and if I zoom it in a bit, okay, you can see uh, that. Let me copy the value as well. Let's me. So this is the output in binary for Newton-Raphson square root for the value of 4. So under root 4 gives us this value. So how do we know that this is how many fraction bits or integer bits? Uh, One way was this. The other way is that you write the outputs. You know the answer for square root of 4 is 2. Okay, so we know in binary that would be what, 1 0. We will count and we will see when we will see 1. Okay, this is 1 and this is 0. So we know this is 2. We will place a decimal point here. Okay, let me put out bigger decimal point. So this is the decimal point. Now we can count 1 2 3 4 5 6 7 8 9 and 10. So now we see that there are 10 for fraction and 10 minus 28, that is 18 for integer. Okay, one way was that we multiplied the answer with the amount of fraction bits that we had. that was one way. So this is how model sim converts binary to decimal. That is why that is the uh, big figure that you're seeing in the model sim. Wait for, as you can see, this should be 1.14 or 1.41, but this is 1458 because there is some multiplication in how model sim converts from uh, binary to decimal. Secondly, if you can place the decimal point here, then why is there a 1? It should be dead 2. Okay, there should be no 1. There should be instead of 1, this should be 0. Okay, because if we, there are 12 stages in our code. As you can see, there are 12 stages. If there were more stages, maybe the answer would become more accurate, but that would mean uh, it will take more time, and as a result, in hardware we see that if the answer is accurate enough, see the answer is accurate to 10th decimal, 10th fraction bit. Okay, so that means it is very accurate. The answer is highly accurate. Okay, it is very, very, very near to the actual answer, but uh, because of how division and how multiplication is performed in arithmetic, in binary, there is some error, because binary, it's not great for calculation. Okay, you can also google why computers are not good for calculation, because there will be some carry on bit. You can do this for hundreds of cycles. You can add 100 stages in Newton Raphson, and if you increase the number of your output bits, and for example you increase the bits to, for example, 50 fraction bits, there will be a 1 in the end. Okay, there will always be something in the end, in the fraction bit. Why is this? There is a very long video on YouTube, you can see if you want to learn about it. But always remember that computers are not great at calculations. There will be some small, very minute, this is very, very close to the answer, but still not accurate. Okay, so this is how we found out. Now coming back to the test bench, I'm going to open up files, TV top level design. You can remove these assertions, we do not need them. Okay, you can also remove this one, you don't need this one. Okay, you can also remove wait for or leave it. Okay. Okay, now coming back, this is the library declaration, this is the entity declaration, this is how visual test bench is written. This is now this is the start of our code. Whenever you see architecture, there will be an end of that architecture. The name of the architecture is test. So this, in this architecture, we will place the whole code. Okay, now this is the component declaration. Component declaration, which is the main design of our file, which from which we will connect our signals to the main, our test bench to the main file. So this is the main file. We just copy it from, if you open up top level design, we can copy this as a whole. Okay, we copy this and we paste it here. Okay, it's all that we have done. Okay, then the second part, we write our own signals. We match the signals of our port. Okay, we make signals of our test bench, because a test bench cannot have inputs and outputs. Okay, it can only have signals in internal signals. No outside thing can come inside or outside. It is just trying to figure out the inputs and outputs for our main design. Then we connect our test bench to our top level design. This is we are connecting, this is called port map. Then we make a clock process. The clock period is 10 nanoseconds, so for half the clock period it will be 0 and 1. As you can see in model sim, it is 0 for half the clock period, and for the next part of the clock period it is 1. So 5 nanoseconds 0, 5 nanoseconds 1. Next, this is the reset. You don't really need it. Okay, there is also a better way if you want to make it more simple for you to explain. You can add reset 1, then wait for 10 nanoseconds, then reset equals 0, and then you can remove this wait for clock period as well, and then you can so there will be 10 nanoseconds reset. Okay, so one clock cycle reset, we can one clock cycle reset. Okay, so then we input our values for x1 and x2 and x3. If you want to add, for example, want to see the uh, square root of 100, just write 100 here and specify the bits. They are already 16 bits, so it is under 16 bits, so that is okay. If you want to enter it, for example, in hex format, you can also do that. Just write x is how you denote hex, then write the value in hex format. For 100 it is 64. Okay, so as you know, the input needs to be 16 bits, and each each character of the hex format is 4 bits. Okay, so remember this: 4, 16, 4, 8, 12, and 16. So that is how you can also send in hex. So we wait for 12 clock cycles, and this process then ends. Okay, so hopefully this concludes your confusions, how many bits there are for integer and how many bits there are for fraction, and how did we calculate this. So if you want to look at from the code, uh, if this is enough, you can stop the video right here, but if you want to look at from the code, there is another way. uh, where was it? You can see these are instantiations. Okay, the first clue that we get, so we have to look for clues. Okay, we do not know, there are no commands, or there, as you can see, these are unsigned or std logic. There are no declarations for fixed point. The only way that you can find out about fixed point from a single piece of code is you look into how they are manipulating the bits. You do not need to know this, but I'm just telling you anyways. Okay, first, uh, there is concatenation, and there we are adding 12 bits, okay, to the input x. And what is srl? Srl is basically a right shift logical operator. So what it is basically doing is it is shifting the bits by to the right by 1, which essentially divides the answer by 2. Okay, so for example, if we have the value 1 0, okay, no, let's do more complicated value. Let's have a value for 4. So 4 equals 1 0 0. If we do an SRL 1, that means shift the right bit, shift the bit to right by 1. So this is basically a command in VHDL. So what we are doing is we are shifting the command. So this will go here and 1 will go here. So this would make it 0 1 0, and that is what 2. So what we did was, by shifting right, we divided the divided 4 by 2. We can do this with any value, it will divide the value by 2. You can do this for 16, you can do this for whatever value, this it will divide it by 2. If you shift it by 1, if you shift it by 2, it will divide by